Picture this. It is 7:58 in the evening. You promised your family you would be home for the evening meal. You are on the 5th floor of an ancient walk-up apartment building. The elevator is predictably out of order. You have a backpack full of groceries and a 2-liter bottle of a chilled carbonated mango beverage that has been shaken violently on the bike ride home. Do you trudge up the stairs and unleash a sticky ceiling-destroying geyser the moment you twist the cap? Or is there an optimal mathematically sound path up the stairs that minimizes the slosh factor and gets you through the door with the drink perfectly calm? This is the stairwell slosh attenuation problem. You are ascending a flight of stairs with a closed cylindrical container of radius 0.05 meters filled with an inviscid incompressible liquid representing the mango drink to a height of 0.20 meters. The container is held rigidly upright, but the motion of climbing imparts a periodic horizontal acceleration to the liquid. The staircase has a standard rise of 0.18 meters and a run of 0.28 meters. You climb at a constant horizontal velocity component of 0.7 meters per second. The footfall impulse generates a primary forcing frequency equal to the step frequency calculated as the horizontal velocity divided by the tread depth. The liquid sloshes with its fundamental asymmetric mode frequency denoted omega-11, which for a cylindrical tank is given by the first root of the derivative of the Bessel function, where the argument equals 1.8412. The dispersion relation for gravity waves in the cylinder is omega squared equals gravitational acceleration times the wave number times the hyperbolic tangent of the wave number times the liquid height. The goal is to avoid resonance where the sloshing amplitude grows catastrophically and the drink explodes upon opening. Part 1 assesses resonance danger. We must calculate the natural frequency of the liquid sloshing in the container in radians per second and the driving frequency of the climb in radians per second. Then we determine the ratio. If the ratio is within 10% of an integer value, resonance is likely. Are you in danger if you walk at 0.7 meters per second? The wave number k11 equals 1.8412 divided by the radius 0.05 meters, resulting in a value of 36.824 inverse meters. The natural slosh frequency omega-11 is the square root of the product of 9.81 meters per second squared, the wave number 36.824, and the hyperbolic tangent of the product of the wave number and the liquid height. The product of the wave number and liquid height equals 7.3648. The hyperbolic tangent of 7.3648 is approximately 1.000 due to the deep water approximation. Therefore, omega-11 equals the square root of 9.81 times 36.824 times 1, which is the square root of 361.24344. This results in a natural frequency of approximately 19.006 radians per second. The step frequency in hertz is the horizontal velocity 0.7 divided by the tread depth 0.28, which equals 2.5 hertz. The angular driving frequency is 2 pi times 2.5, which equals 5 pi or approximately 15.708 radians per second. The ratio of the natural frequency to the driving frequency is 19.006 divided by 15.708, which equals approximately 1.21. This ratio is 1.21, which is 21% away from the integer value of 1.0. Since it is not within the 10% threshold, you are technically safe from catastrophic primary resonance. The ringing will still be noticeable and somewhat irritating, but you are not in immediate danger of a ceiling repainting project. Part 2 demands the optimal ascent velocity. To save your ceiling paint and your dignity, you decide to alter your pace. Assume the relationship between horizontal velocity and step frequency is fixed by the staircase geometry. You must find the exact horizontal velocity you must maintain so that the step frequency is exactly 1/2 of the slosh frequency. This subharmonic safe zone minimizes energy transfer and is a stable island in the parametric oscillator plane. We set the angular step frequency equal to 1/2 of the natural slosh frequency omega-11. We know the angular step frequency is 2 pi times the linear frequency, and the linear frequency is the horizontal velocity divided by the tread depth. Substituting these relationships yields the equation 2 pi times the quantity horizontal velocity divided by 0.28 equals 1/2 of 19.006. We solve for the horizontal velocity by multiplying 19.006 by 0.28 and dividing the product by 4 pi. The numerator calculation is 0.28 multiplied by 19.006, which equals 5.32168. The denominator is 4 times pi, which is approximately 12.56637. The quotient of 5.32168 divided by 12.56637 yields a velocity of 0.42348 meters per second. Rounding to 3 decimal places provides the final optimal horizontal velocity of 0.423 meters per second. This is the ninja tip toe velocity. Walking at this precise speed ensures that the forcing from your footsteps interacts with the liquid wave in a manner that cancels out the resonant growth rather than amplifying it. The fluid mechanics inside the bottle will remain laminar and the pressure at the cap interface will not exceed the saturation threshold for the dissolved carbon dioxide. You will look somewhat unusual moving at this specific deliberate cadence up the stairs, but the mango beverage will be as serene as if it had never been transported. Upon reaching the apartment door, you will be able to open the bottle with confidence, resulting in a gentle hiss of appreciation rather than a tropical storm of sticky regret. The application of Bessel functions and parametric resonance theory to daily pedestrian logistics demonstrates that mathematics is not merely an abstract pursuit confined to textbooks, but a practical survival tool for navigating the complex hydrodynamics of grocery transportation in vertical urban environments. The next time you are faced with a broken elevator and a carbonated beverage, remember the number 0.423 and know that calculus has your back. You may arrive a few seconds later than your brisk walking counterpart, but you will arrive with all 2 liters of your beverage intact and your dignity fully preserved. The walls and ceiling of your stairwell will remain free of artificial mango colouring, and the only thing you will need to worry about is reheating the food. This concludes the analysis of the stairwell slosh attenuation problem. Walk safely and let the Bessel functions guide your feet. Your smartphone is a slab of dark glass lying flat on a windowsill, slowly starving for photons, while the sun blazes just outside its narrow field of view. You could prop it up, but at what angle too steep, and you lose the winter sun hugging the horizon too shallow, and the high summer noon glances off like a skipped stone. You are not looking for the daily adjustment of a motorized tracker, you want the other, sacred set it, and forget it eternal fixed tilt angle that maximizes the total energy harvested over an entire calendar year from that exact spot. Welcome to the intersection of orbital mechanics, integral calculus, and the universal human condition known as low battery anxiety, the problem, the fixed tilt dilemma. Assume you reside at a latitude of 34 degrees north, a lovely place with distinct seasons. Let us call it Halal Cart Central. You have a perfectly south-facing window with a deep sill. The glass is optically perfect, and the window offers an unobstructed view of the sun path from sunrise to sunset every single day of the year. You are holding a small flat solar panel. You are going to place it on the sill at a fixed tilt angle theta measured from the horizontal, so theta equals 0 degrees means flat on the sill. Looking straight up, theta equals 90 degrees means vertical against the glass. You will not touch it for 365 and 1/4 days. The sun apparent position in the sky is governed by 2 main angles: the solar declination delta, which varies sinusoidally with the day of the year n, where n equals 1 is the vernal equinox March 20th, given by delta of n approximately 23.44 degrees times the sine of 360 degrees divided by 365.25 times n, and the hour angle omega, which runs from sunrise to sunset. The instantaneous power hitting the panel is proportional to the cosine of the angle of incidence gamma between the sun rays and the vector normal or perpendicular to the panel surface. When the angle of incidence is 0, the rays hit dead on. When it is 90 degrees, they graze the surface uselessly. The mathematical relationship for a south-facing panel is governed by the spherical law of cosines. Cosine gamma equals sine delta times sine of phi minus theta plus cosine delta times cosine of phi minus theta times cosine omega, where phi is your latitude, 34 degrees north, theta is the panel tilt angle from horizontal. What we are solving for delta is the sun declination on day n, and omega is the hour angle where sunrise occurs at omega subscript s and sunset at negative omega subscript s. Since we only harvest energy when the sun is up and the angle of incidence is less than 90 degrees, meaning cosine gamma is greater than 0, the total annual energy E collected is proportional to the double integral over all days and all daylight hours of cosine gamma. Your mission, should you choose to accept it and impress the algorithm, is to determine the optimal fixed tilt angle theta subscript opt that maximizes this total annual energy integral for a latitude of 34 degrees north. You may assume a simplified clear sky model where the atmosphere is perfectly transparent, no air mass effects, just pure geometry, and you may use the analytical approximation that the annual average of the square of the sine of the declination angle averages to a specific constant value due to the Earth tilt. Find theta subscript op show that this value is not simply equal to the latitude of 34 degrees, but rather a slightly steeper or shallower value due to the geometric weighting of the longer days of summer versus the shorter days of winter. Provide the final angle to the nearest tenth of a degree, and explain why a fixed panel prefers to be a little greedy for winter sun or a little relaxed for summer glow. The setup for the integral, the math you will do, the daily insolation h on day n is the integral of cosine gamma from sunrise to sunset. H equals the integral from negative omega s to omega s of sine delta sine phi minus theta plus cosine delta cosine phi minus theta cosine omega s d omega, integrating with respect to omega, where the integral of cosine omega d omega is sine omega, gives h equals 2 omega s sine delta sine phi minus theta plus 2 cosine delta cosine phi minus theta sine omega s, where the sunset hour angle omega s is determined by setting the sun elevation to 0. Cosine omega s equals negative tangent phi times tangent delta, the yearly averaging trick over the course of a year delta oscillates between negative 23.44 degrees and positive 23.44 degrees. Since we're looking for a fixed theta, we need the yearly average of h